Hi, my name is Sue. In this lesson, we'll look at the graphs of quadratic functions called parabolas, and we'll look for patterns which will help us to graph them, and learn to find the vertex of a parabola. We'll also look at a model for optimization. Quadratic functions. A function f is a quadratic function if f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a cannot be 0. The most basic quadratic is the function f of x equals x squared. It is graphed in blue. Let's compare it to other equations and their graphs to look for patterns to help us graph parabolas more easily. The first pattern to study is what happens when the leading coefficient a is not 1. In our example, we see that a is a fourth. What happens is that all of the original y values are now being multiplied by a fourth, which shrinks them down to look wider than the original blue graph. If a was a value greater than 1, then all of the y values would be multiplied by that value and get taller, which would make the graph become more narrow than the original graph. The third concept to think about with the leading coefficient is looking at what happens when a is negative. So if we let f of x equals negative a squared, then we would take all of our y values in the blue graph and graph the opposite of those. Or what it would do is turn the graph upside down. It flips it over the x-axis. Next, we'll look at added and subtracted values to our quadratic function. In the second function, a 4 is being added to the original function. Comparing the two graphs, we see now that the new red graph is shifted 4 up from the blue graph because of the added 4. If 4 were subtracted, then the graph would be moved down 4. Horizontal shifts are a little more confusing. This time, a number has been added inside the function. In this case, inside the squared portion. This affects the graph in the horizontal direction by moving it to the left 2. If it had been a subtracted 2, then the graph would have shifted 2 units to the right. This is the opposite pattern from what would feel more natural, as in the last example, where an added 2 went up and a subtracted 2 would go down. Now let's look at graphing a parabola using all of the patterns discussed. If we compare our function to the smallest function, f of x equals x squared, we can see that there are 3 transformations occurring. The first is a multiplied 3. This will take all of the original y values and multiply them by 3, causing the graph to be stretched vertically. The second transformation is this added 4. This will cause the graph to be moved left 4. Since the 4 is with the x, it transforms it in the horizontal direction. The added 5 on the outside causes the graph to move up 5. So let's take a look at the final graph. Instead of having our next set of points right here, they've been multiplied by 3, so they've been stretched upwards. The added 4 has caused our graph to move to the left 4. The added 5 has caused our graph to move up 5. So this blue graph is the final graph. And looking more closely at the graph and our equation, we can see that the vertex of our parabola is -4, 5, and that our graph opens upwards because our leading coefficient is positive. This leads us to some general principles for the graphs of quadratic functions. The first principle is the graph of a quadratic function is defined by f of x equals a times the quantity x minus h squared plus k, where a cannot be 0. This is a parabola with the vertex at h, k, and the vertical line x equals h as its axis of symmetry. 2. The graph will open upward if a is positive and downward if a is negative. And 3. The graph is wider than that of the base graph, which is f of x equals x squared, if the absolute value of a lies between 0 and 1, but the graph will be narrower than that of f of x equals x squared if the absolute value of a is greater than 1. To make our equation easier to work with, I'll exchange f of x for the letter y, giving me y equals x squared minus 2x plus 3. Now since we need to complete the square for x, then we'll go ahead and move the 3 to the other side, leaving y minus 3, and I'm going to go ahead and leave a space here, equals x squared minus 2x. So completing this square, we have half of negative 2, which is negative 1, and then we need to square it, which gives us a positive 1, which I also need to add to the other side. This gives me y minus 2 equals, and the reason that I added the 1 is so that I can form a perfect square. So we have x minus 1 squared. So solving for y, we get quantity x minus 1 squared plus 2. So from this form, we can see that our vertex is the opposite of this value and the same as this value. Or the vertex is the ordered pair 1, 2. So the vertex formula gives us a formula to find the vertex of the graph of f of x equals ax squared plus bx plus c, where a is not 0. The formula that we would arrive at after completing this square would give us these coordinates, where the x value of our vertex would be the opposite of a over 2b, and then to find the matching y value, we would plug in the x value into our function. Now we have a more complete picture of how to approach graphing a quadratic function. Step 1. Decide whether the graph opens upward or downward. Determine whether the graph opens upward if a is greater than 0 or downward if a is less than 0 to aid in the graphing process. Step 2. Find the vertex. So find the vertex by either using the formula or by completing the square. Step 3. Find the y-intercept. Find the y-intercept by evaluating f at 0, or letting x be 0. Step 4, find the x-intercepts. Find the x-intercepts, if there are any, by solving f of x equals 0. Step 5, complete the graph. Find and plot any additional points as needed, using the symmetry about the axis of symmetry. Following our new set of steps, since a is positive, we know the graph will open up. Step 2 is to find the vertex. Now we can either complete the square or we can now use the vertex formula. So if I use the vertex formula, I'm looking for the opposite of b over 2a, which is the opposite of negative 2, which is 2, over twice a, and a is 1. So this will give me 1. So plugging 1 in to the function will give us the matching y value. So we have 1 squared minus 2 times 1 plus 3, or 1 minus 2 is negative 1 plus 3 is 2. So we have a vertex of 1, 2. So plotting the vertex and realizing that it opens up, we see that there's no x-intercepts. But we do have a y-intercept, which is step 3. To find the y-intercept, we let x be 0. So letting x be 0, we see that our y-intercept is 3. And since our axis of symmetry is a vertical line that goes through our vertex, we can find a matching point on the other side of our y-intercept. This will allow us to get a sketch of our parabola. Finally, let's take a look at what is called an optimization problem, where we need to find the largest or maximum value or the smallest or minimum value. Example 4. A projectile on Earth is fired straight upward so that its distance in feet above the ground, t seconds after firing, is given by s of t equals negative 16 squared plus 400t. We're asked to find the maximum height it reaches and the number of seconds it takes to reach that height. If we sketch just an idea of what the graph would look like, making the horizontal axis the time and the vertical axis the height, then we would see that this is a parabola that opens down. Therefore, it would have a maximum height at the vertex. So since we only need to find the vertex and we don't need to find anything else, then the easiest way to find the vertex is by using the vertex formula. Instead of x, I have a t. So t is the opposite of b over 2a, which is the opposite. This is b. C would be 0 if you had another term. So the opposite of 400 all over twice negative 16, which gives us 12.5. Now plugging 12.5 back into the original equation, so s of 12.5, it would look like negative 16 times 12.5 squared plus 400 times 12.5 gives us s at 12.5 is 2,500. The projectile then will reach a maximum height after 12.5 seconds, and the maximum height is 2,500 feet. In this lesson, we looked at the graphs of quadratic functions called parabolas. We looked for patterns, which helped us graph them, and we learned how to find the vertex of a parabola. We also looked at a model for optimization. Now it's time to go into the homework section and work some problems on your own.